Then we take another small problem. Here, the problem says a light rod. Note this word right. Light. A light rod means we have to assume in our calculation the mass of the rod is to be neglected. Light rod of length 1 meter is pivoted at the center. That means its axis is at the center and has two masses of 5 kg and 2 kg are hung from the two ends. So we can take a light rod, like this, okay? Then there are two masses with a little string, some kind of a string, etc. There are two masses. One mass has a 2 kg mass. It's a 2 kg mass. Let's say it is 2 kg hung here. And another is a 5 kg mass, a little bigger. The 5 kg mass. And length of the rod is 1 meter. It's the fulcrum is at the center. So this is 1 meter. So naturally this is 0.5 meter and other side is also 0.5 meter. So this is the system. Find the initial angular acceleration of the rod, assuming that it was initially horizontal. Obviously, if you make an arrangement like this, the rod will start moving in this angular direction. That is because on the right hand side, this 5 kg. And the 5 kg mass will go down and the 2 kg mass will go up. Right? So, first question is find the initial angular acceleration. That is all that they want to know. That is all they want to do. So, this 5 kg mass, it gives a torque of clockwise direction. And torque of the 2 kg mass is anti-clockwise direction because it goes upward and this goes downward. So let us say torque of 5 kg mass, torque is equal to the force multiplied by the perpendicular distance. So for your recovery of memory, I write it down. Force multiplied by perpendicular distance. This is equal to, force is here 5g and perpendicular distance is half meter. So this is 5 by 2g. This is the torque. And the torque of 2 kg mass similarly is 2g multiplied by half is equal to 2g by 2, 2g by 2. Now for mathematical understanding, we normally write it this way. If this torque is clockwise, we give a clockwise symbol here. If this torque is anti-clockwise, we give an anti-clockwise symbol here. So that you can always remember how to, if you want to revise this problem later on, it will be easy for you. So the net torque is equal to 5g by 2 multiplied by 2g by 2 equal to 3g. And the net torque is clockwise. This is how we mathematically designate it. Now we also have to find out the moment of inertia of the system. Moment of inertia. What is the moment of inertia? moment of inertia. Now, this is a very light rod, so we don't have to consider the mass of the rod. So we just have two masses, 2 kg and 5 kg. Both are 0.5 meter away from the center. So moment of inertia is equal to 5 kg multiplied by half square. Moment of inertia is mr square plus 3k plus 2 kg m into r square half square is equal to, it is equal to 5 by 4 plus 2 by 4 equal to 7 by 4 kg square. So this is the moment of inertia. Remember, the torque is force multiplied by distance. So you have to write 5g. But the moment of inertia is mr square. So you have to write only 5. There is no use of g here. Now we know that torque is equal to moment of inertia I into alpha. Using this equation, what do we do? Torque is 3g by 2. So 3g by 2 is equal to moment of inertia is 7 by 4 multiplied by alpha. Alpha is the angular acceleration. From here we get alpha is equal to 3g by 2 multiplied by 4 by 7. So this is equal to, here we have 2. This is equal to 6 by 7 g. If you put the value of g as 9.8, so okay, let's write 6 by 7 into 9.8. This you will find this value is 8.4 rad per second square. Since it is acceleration, it is 8.4 rad per second square. So this is the answer. The question was not at all difficult. But why we took up this question? Because this question has a tail end, because there's a next question in your textbook is actually connected to this question. So we took up this question first. The next question says, suppose that the rod in the problem 31 has a mass of 1 kg. Now the rod has a mass of 1 kg. So you have to consider the mass of the rod also while calculating the moment of inertia. And the mass is distributed uniformly over its length. Find initial acceleration of the rod and something else. Okay, let's find the initial acceleration. Here we have found initial acceleration alpha. Here we have found acceleration alpha. Here we have found acceleration alpha considering initial acceleration alpha, considering there is no mass of the rod. Now we have to do the same calculation considering there is a mass in the rod. The same calculation considering there is a mass in the rod. Let's do this way. Let's draw this figure once again. That will be very useful. Let's say this is the rod. Let's say this is the rod, right? Let's say this is the rod and the two masses like above. There is a 2 kg mass and there is a 5 kg mass. Once again, similarly, it is pivoted at the center. This length is 0.5 meter and this length is also 0.5 meter. Now, this rod has a mass of 1 kg. Rod mass is equal to 1 kg distributed over its length. So, last time when we calculated moment of inertia, remember, we only calculated the moment of inertia of these two masses. Moment of inertia of these two masses. Now we have to do the same calculation with the moment of inertia of the rod also. That's the difference, right? So here, what is the moment of inertia here? Moment of inertia is equal to, the two masses are there already. So this is 5 into half square as usual, plus 2 into half square as usual, plus the right side of the rod side. Let me write here, that may be beneficial for you. Side of the rod, its moment of inertia. Now here, this part of the rod is actually rotating on an axis passing perpendicularly to one of its ends. So this moment of inertia is given by the equation 1/3 ml square. 1/3 ml square. So this is equal to, this moment of inertia is equal to 1/3 into m. What is the m? The rod has a mass of 1 kg. So its mass of the half of the rod is half kg. So half kg. Length of the rod, L, is half meter. So it is half square. Half square. This becomes 3 is a 2, 6 is a 4, 24. This becomes 24. 1 by 24. This is the each part of the rod. 1 by 24. So this 1 by 24 gets added here. 1 by 24. Twice it gets added. Once for the left hand side, once for the right hand side. This is equal to your 5 by 4 plus 2 by 4 plus, this is 1 by 24 and 1 by 24 plus 1 by 24. If you calculate this, it becomes, your LCM is 24. 4 the 6 is 20. 4 the 6 into 5 is 30. Plus 4 the 6 into 2 is 12. Plus 1 plus 1. This is equal to 30 plus 12 is 42 plus 1 is 44. So this is equal to 44 by 24. You can divide both numerator and denominator by 4, so it becomes 11 by 6. So this is the moment of inertia, 11 by 6 kg meter square. Earlier moment of inertia was 7 by 4, now it is 11 by 6. That is the difference it has made. And torque was, remember, torque was 3g by 2. So there is no difference in the torque. So you use this moment of inertia with the torque 3g by 2. Right? Therefore, now if, once again, alpha, now if, right here, if alpha is the initial acceleration, then torque was 3g by 2 is equal to moment of inertia 11 by 6 into alpha. From here we get alpha is equal to 3 into g, I take 9.8, that multiplied by 6, that divided by 2, that divided by 11. If you calculate this, it will be 8 rad per second square. So this is the answer. But this question has a second question. Tensions in the supports to the blocks. This is the tail end question. Now, these two blocks, what do you find? These 5 kg blocks will start moving downward and 2 kg block will start moving upward. Right? And with an acceleration, this acceleration has to be same for both of them because it is there connected to a rod with an acceleration. What is this acceleration? How much is this acceleration? This acceleration is related to this angular acceleration alpha. This acceleration can say upward, upward, or downward acceleration of the masses we designated by A, linear acceleration. Downward acceleration is equal to, this acceleration is equal to, A is equal to, R alpha, radius of rotation into alpha, is R alpha. R is 0.5 or half. So half into 8, alpha is 8, equal to 4 meter per second square. So upward or downward acceleration is 4 meter per second square. Once you've defined this upward and downward acceleration, then you go to define the other aspects of this motion. If you consider the free body diagram of this 5 kg mass, there is the upward tension T, right? And there is a downward gravitational force which is equal to mg. Now here, if we equate for the 5 kg force, for the 5 kg mass, we'll find the upward tension T will be equal to, there are two downward forces, mg and ma, is equal to mg plus ma. Right? Here, no, sorry, I have done a mistake. Once again, I am sorry here. Here, the upward tension T will be mg, or rather, I put it this way. I rewrite the equation this way. Considering the free body diagram of the 5 kg mass, what you find that ma and that ma is equal to mg minus tension. Because mg is working downward, there is a tension upward. The difference of these two creates the downward acceleration ma. So from here we find the tension T, let us write T5, the tension in the 5 kg mass. Tension T5 is equal to mg minus ma, equal to 5 into 5 into 9.8. 5 into 9.8 minus 5 into minus 5 into A is 4. This is equal to 5 into 5.8. If you calculate this, this will be 29 Newton. One answer. But the situation is slightly different in case of the 2 kg mass. Difference in the way it is in the reverse direction. For the 2 kg mass, for the 2 kg mass, it is different. For the 2 kg mass, there is also, once again, there is a tension T. Here, tension T minus, here the equation is tension T2, that means mass tension in the 2 kg mass, tension T2 minus 2G, because T2 acts upward, 2G acts downward, is equal to A. Acceleration upward, because it is moved upward to A. So therefore, we get T2 is equal to 2G plus 2A is equal to 9.8 plus 2. So this is equal to 2 into 13.8. If you calculate this, this is 27.6 Newton. So these are the 4 answers. Now the 2 answers. The tension in the 2 blocks and the initial acceleration is 8 rad per second in this particular case. Okay. Now we shall go to the next question. Quickly we shall go to the next question.